Hey, what's going on, guys? Occupancies here. In this video we're going to be running a function in order to being able to parse FEN strings representing board position. So the very first thing I would like to consider is actually to paste a set of FEN position I'm used to work with during developing a new chess engine. So we have an empty board here, a start position, so-called tricky position to track the most available bugs in the mode generator, killer position to keep track of the number of in order to keep track of the process of reducing the number of traverse nodes within the alphabet of search, assuming that we're ordering the killer moves produced by the beta cutoffs, and this position actually has those beta cutoffs to oh my god, to have this. Okay, forget that. Just the killer position would be needed later on for the search purposes, and so-called CMK, kind of code making position, is another position I'm using to test in order to test the search function. So that doesn't really matter that much. So let me quickly walk through the format of the FEN string itself. So we have up to 8 ranks being represented, starting from the 8th rank, then 7, 6, 5, 4, 3rd, 2nd, 1st, and then we have the side to move, then we have the castling rights, if available. If not available, just the dash, and then we have the impedance square. If available, it's the square. If not, it's just a dash, and some half move counters that we don't really kind of care about, at least at this moment. So all we would be parsing is the board position, side to move, castling rights, and the impedance square, and that's it. So if we have ASCII character represented piece, that means that there is a piece on a corresponding square. So here we have files like A, B, C, D, E, F, G, H file. So if piece is on the file, we have a letter. If we have some empty square, we have this number. So this is the same as if we just write the FEN like this. So we can use 1 in order to represent the empty square, but also people used to do it like this, so just using the numbers to represent the number of empty squares. So that's kind of it. So yeah, I think this is it regarding the explanation how the FEN string is composed, and now we can actually go for implementing our parse FEN routine. So I just want to scroll down to input and output section of the source code, and here after the print board, just right over in here, I will start implementing my parse FEN string routine. So this would be the void parse FEN, and it would be taking the character pointer to the FEN string itself. So the very first thing to consider regarding initializing a board with a new FEN string is actually to reset board position and state variables. Let's call it like this. So I would be making use of the memset function, and first, so let's scroll up where we have the board definition. So we need to initialize all the bitboards to zeros, all the occupancies to zeros. We can drop the side because anytime we would be initializing this either to white or black, but still for clarity I will leave that. We need to initialize the impedance to no square and castling to 0 to make sure that none of the sides is available to castle to none of the directions. So bearing this in mind, let's go for our initialization stuff here. So memset bitboards with a 0 unsigned lon and the size of bitboards, and then the same for the occupancy. So memset occupancies and 0 unsigned loan and the size of occupancies. Okay, and then let's make its side equals to 0. So, well, actually, let me provide a separate commentary. So let's say reset board position. And here, I mean, like bitboards. Then we want to reset occupancies, and again, like bitboards. And then we want to reset side to move, and or maybe like let's call it reset game state variables, maybe like this. So side would be equal to 0, in peasant would be equal to no square, and castling right would be equal to 0 as well. So I just want to open the terminal in the current working directory to make sure it still compiles and runs. So make debug to compile the source, to build the source, and if it compiles, I want to run the BBC binary executable here. Okay, and it seems everything is still kind of working. Okay, yeah. So I don't really want all this stuff from the previous parts, so let me drop this manual board position initializing stuff here, and we'll have only 2 function calls here, so parse FEN and print in the board. So let's parse the FEN, and let's start with the so-called tricky position. Okay, and as far as we have this tricky position as just the definition of the string, this means that we're already passing the pointer to the string to our parse FEN function. So let's have a look at this. We have this character pointer to FEN. So this is it basically. And now we need to loop over board ranks and files, just like we're doing this all the time. So for int rank equals to 0, rank is less than 8, and rank plus plus, the same for the files. Okay, so the same for the files. I'm sorry, rank file. Now, as always, we need to initialize current square, so just converting the files and ranks into a square. So integer square is gonna be equal to rank multiplied by 8 plus file. Okay, and now I just want to make sure that it still compiles and runs. Okay, so the next thing to consider, we need to match ASCII characters. So ASCII characters within FEN, or just ASCII pieces within FEN string. So we can say if and the pointer to FEN is greater or equals than A, and pointer to FEN is less equals than Z, like this. Okay. Or the same, but for for uppercase letters. Oh, what have I done? Okay. And now we can initialize our current piece type. So initialize piece type, and let's create the integer piece, and it would be equal to character pieces. So that's the variable we've been defining a couple videos ago. So here is the character pieces. So the idea is to convert this ASCII characters from the FEN string to the encoded values and use them as an indices to index bitboards. So okay, indexed by the pointer to FEN like this. So this is the current character, and now we want to set piece on corresponding bitboard. Okay, so we can simply say set bit and bitboards indexed by the piece at the current given square. And after this we want to increment pointer to FEN string, or in other words, we just we just incremented the pointer. I don't know how to call this in a different way. So pointer to FEN plus plus, and now already it should be printing at least some pieces, probably in a wrong order. Yeah, so at least the one rook is printed. So the idea why it only prints the rook and then drops without taking care of the other pieces, that's because it doesn't know like what to do with this numbers. It's not parsing them. But I guess if we just try to print this start position, it should print all the pieces because no empty squares here. But let's get back to our tricky position. And find a parse FEN. So the next case to match, we want to match empty squares, empty square numbers within FEN string. So if pointer to FEN is greater or equals than 0 and pointer to FEN is less equals than, oh, not like this, sorry, than 0 and less equals than 9. So in this case we want to initialize offset variable. Well, not it's the variable obviously, but just what I want to say. So let's create the int offset, and it would be equal to pointer to FEN minus 0. And this is a trick to simply convert the character of 0 to the integer of 0. So let's actually specify this here. So convert character 0 to integer 0. Okay, so in this case we would be able to use this offset to alter the current square. So we can simply say like adjust file counter. So we can simply say file plus equals this offset to skip those files that we don't really need to take care of. So that means that the next iteration, this int square would be already different, like assuming this little file offset. And at the very last we need to again like to increment pointer to FEN string, and then we'll add a little more condition here, but for now I just drop it to because you know, like, if you're implementing this parse FEN for the first time ever and you don't know this tiny little trick, it might be challenging to get an idea like what's going wrong and why the FEN is not getting parsed correctly. So I will add just some piece of code here as well, and but before that we also need to match a rank separator. So we can simply say if pointer to FEN is equal to this slash. What we need to do in this case, well, actually in this case we need again like simply to increment our pointer to FEN. Actually no need for curly braces here. So this like this is almost it, but the position is not correct. So if we just have a look at this position in, let's say the arena GUI, you will now realize that the position is actually kind of wrong there. So I just want to grab this tricky position, just want to grab this tricky position, copy and paste to the arena GUI. So if we just compare this to positions, you see like it goes okay until this rank, but starting from this rank it just shifts one cell, one square to the right, which is obviously wrong, and it doesn't really have to be like this. Also this pawn is misplaced, and also so the reason why this is happening, and again, like if you've never been parsing FEN before, this might be a little bit of a challenge to discover like why this is actually happening. So the reason is following. So if we have our empty squares followed after a piece, then it works just fine. But if we have an empty square, then it still kind of increments the file, because it increments the file every time the loop occurs, every time we loop over the files, and that's the reason this shift happens actually. So in case if we don't really have, so in case if we do encounter this, let's go to parse FEN. If we do encounter our number, but we don't have a piece on whatever bitboard at the current given square, in this case we need to decrement the file. So now let's try to implement this. So we just reference our print board function, then we have this loop over the bitboard. So I just make use of it right over in here as well. So here, okay, and piece. So we're defining the piece variable equals to -1, then looping over all the bitboards available, and if the piece is available, we actually initialize this. But why do we need this actually? So here we can simply say like if no piece on current square, let's just say like no piece on current square, well, or okay, maybe if no piece. So if, and I just say if piece equals -1, which means that here within this loop and within this if statement nothing really happened. That means that we have the empty square on this piece, and that's the reason to say simply like file minus. So if we just have a look again, now the position is already correct. So let's compare this. So you see like this pawn is on d5 as expected, then the knight, this pawn is on h3, so the position is just right. I just forgot to add a little bit more commentary, so both in brainboard and so and in the parse FEN. So if piece, so how I call this actually, I didn't call it yet. Okay, if there is a piece on current square, we want to get piece code, and the same here. So if there is a piece on current square, we want to get piece code, and if the piece code is equal to -1, so that means like no piece is available on whatever of up to 12-bit boards. In this case, we know that this is the empty square. Let's even say on empty square, on empty current square. Okay, we want to decrement the file. Okay, so this is kind of it, and obviously we didn't yet take care of our game state variables. So after the for loop kind of ends here, I just want to print the FEN string, so just to visually see where the pointer is now available at. So let's print this as string and FEN without the star, because I want to print I'm passing the pointer to match this specifier to print a string actually. So let's have a look. And FEN, so it starts with, well, it actually starts, let me just enclose this within quotes to give you an idea. So we have an empty space and then the side to move and so on. So we need to skip this empty space, and in order to do this we need simply to again like increment pointer to FEN string. And the idea for doing this, well actually let's say parse, let's say go to parsing side to move, and in parentheses just what in particular this is actually. So we do this one more time, we have already this this sort of a W here. So we will always have either W for whites or B for blacks. So now we can already parse side to move. So we can actually say like pointer to FEN equals to white, like this. Yeah, let's enclose this in parentheses to make sure it's safe. In this case, we want to set our side equals to white, and otherwise probably enclose within the parentheses as well. And otherwise we want to say that side actually equals to black, equals like this. Okay. Okay, so side equals to white, and now let's just try to play around with this FEN string a little bit. So I just copy this and pass this directly just to manipulate this a little bit. So let's try to change this to black. Okay, now it changes the color to black, which is quite pretty nicely. Okay, so then we go for parsing our castling rights. So to make sure we do parse our castling rights. So let's have a look. So now we need to skip up to two indices within this FEN pointer, within the FEN string, that the part of the FEN string that has left already. So let's say go to parsing castling rights. Well, it's actually also regards the increment of the pointer, but here we're not saying like FEN plus equals to. It won't work. We need to say FEN plus equals to, and the difference is that here we work with a pointer directly, and this, well, this is just this is how this has to be done. I mean, just that's I just want to show you this visually. So from now on we are already here with having our castling rights at where the pointer points, basically. Okay, so the next thing to consider would be actually parse castling rights, and here we need to loop to make a while loop. So while pointer to FEN is not equal to empty character to empty space, and then we want to increment our pointer, and here we want to switch this pointer to FEN, and case this might be either white king. So in this case we want to bitwise or our castling variable with yeah, if I could only remember what in particular, probably with 1. So castling rights, so white king, so 1 2 4 8, yeah, parse FEN with 1. I don't even need to say this. I can simply say like white king, white castling king side, and then break, and copy. Same for white queen, and like this. Then the black king, and like this, and black queen, and like this. And in case if castling is not actually available, we want simply to break. So in case of dash, like this. So let's have a look. Okay, now we have all the castling rights being available, and let's check if this is like so. Okay, so let's try to drop one of them. Okay, so they have been parsed appropriately. Okay, dropping this one. Okay, let's drop another one. So only black king castles king side. Okay, and if nothing there available, also, yeah, this is also just kind of fine. Okay, so now we can go parsing our in peasant square. So parse castling rights, go to parsing castling rights, and go to parsing in peasant square. Okay, so yeah, now it's within the in peasant square. So here we can simply, so yeah, parse in peasant square. So we can say if pointer to FEN is not equal to dash, in this case we provide our logic, and on let's just say like no in peasant square. So in this case we say else and in peasant equals to no square. Save. Okay, so let's have a look. Yeah, so now we are at the in peasant and we actually drop here. Okay, perfect. So no square, and don't need this stuff anymore. So now we need to parse our file, parse in peasant file and rank. So int file would be equal, so we can reference FEN as an array here. So FEN 0 minus 0 to convert the file into an integer, and also int rank, and here we need to say 8 minus, so this is the same when we were printing the ranks, so because the loop starts with rank 0 to 8, not 8 to 1. So the same here, so 8 minus FEN the next index, so FEN at 0 is just the current pointer to FEN, so it's the same as if we just print in like pointer to FEN, and this one is the next index, is the pointer to the next element from the first from this one where we're now, so minus 0 as well, and initialize in peasant square. So we can simply say in peasant equals rank multiplied by 8 minus, plus file, and this should work in theory. So let's try to set some sort of an in peasant square. Well, let's try to set, say, only king-side castling for white on black to make sure it works. Okay, and let's try to set in peasant square, say, to E3. So okay, something has gone wrong. Let's have a look why this could have happened actually. Oh, obviously minus a, that's what have I done? Yeah, minus a. So yeah, now it prints this E3, just exactly the square that we have here. But obviously first it converts this to the square, and then within the print board, as you remember, we're actually converting this to whatever square we want to convert to coordinates. Yeah, so it seems like in peasant parsing works perfectly well. Well, okay guys, so this is almost it, and there is a couple more things we actually need to implement within our parse FEN function. So remember that we keep track of the occupancies. So the idea is to actually initialize our occupancies for white pieces, for black pieces, and for both sides. So let's get started with initializing, let's say initialize white occupancies, and let's make a loop. So integer piece equals to white pawn, piece is less equals than white king. So loop over the white pieces. Let's actually specify this. So loop over white pieces bitboards and piece plus plus, and here we want to initialize white, or it's better to say populate white occupancy bitboard, and we can reference occupancies by white, which means 0, and we want to bitwise OR it with the bitboards indexed by the piece. And if I did everything correctly, in theory it should print. So I just want to print, let's print white occupancies and print bitboard and occupancies and white. So it now should print only where the white pieces are. So let's see. Okay, rooks, king, so all pieces, all the pieces on the second rank. So we have this knight, queen, and 3 pieces here. Yeah, it seems like it's quite pretty nice already. And also we need to do the same for black pieces. So loop over black pieces bitboards, so black pawn, black king, and occupancies indexed by 1 or black. So okay, let's print them as well. So print black, let's put this before actually, print black occupancies and print bitboard occupancies indexed by the black color. Okay, so here are the black occupancies. So rook, king, rook, 1 0, all ones, 0, third rank bit 0 0, 3 bits. Okay, then 1 bit here and 1 bit here. Yeah, perfect. And the very last one, in order to get the occupancies for all the pieces, we can simply bitwise or all occupancies, both occupancies with white and black occupancies. So well, we could have done this, well, doesn't matter, we can do this like this as well. So populate, or let's say initialize all occupancies, and occupancies indexed by both, we need to say like bitwise OR equals occupancies indexed by white, and the same, well, probably I could have made this as a one-liner, but just for clarity I want to make it this like way with the black pieces. Okay, and let's print all occupancies. So print bitboard and occupancies and both. So let's have a look. Okay, it seems like, so let's reference the arena GUI to make sure I didn't miss anything. So we got this rook, okay, 2 pieces, okay, 1 piece, empty squares, okay, 1 1 okay, all pieces. Yeah, it seems like it is okay. And one last test, because if you're about to be running to be calling this parse FEN only once, we cannot check whether how it deals with some sort of a different positions. But in this case, in case of the UCI protocol, bearing UCI protocol in mind, it might happen that we would be calling parse FEN many times within a single given session of our chess engine running. So we need to make sure that every time we do this, everything actually kind of works. So and the FEN is parsed correctly. So let's start with a start position. Okay, and here we got, okay, so we got our white, no in peasant, all castling rights, white occupancies, black occupancies, both occupancies. Okay, and now let's go for same but for tricky position, and let's go. So we started here, initializing everything, then we have this position, okay, and yeah, black, white pieces, and both. Yeah, it seems to be right. And let's also do the same for CMK position. Hold on a sec. Here, nope, here. Okay. So this is the CMK position. Okay, so black pieces. Yeah, it seems like fine. Okay, white pieces. Okay, and both pieces. Yeah, so it seems like it's working quite pretty nicely. So I just want to check this out visually one last time before we finish this video. So, oh my god, not like that. So we need to make sure that we reset all the bitboards, okay? That we reset all the occupancies, and then we reset the side to move in peasant square and castling. I just didn't notice. So here we have all the castling rights, no in peasant. Well, it's a little bit. So I just also want to test if the in peasant and castling been reset correctly. So let's grab the tricky again and replace it here. And I just want to make some custom castling rights, and the in peasant set to say e6, e3, e6, doesn't matter. So okay, hold on a sec, why don't we have castling rights? Okay, is this a bug? Okay, so we have all the castling rights now in peasant square. Well, as far as the occupancies, seems to be working quite pretty nicely. I just want to drop them because they take too much space. Well, I can leave them at the very end. Okay, so parse FEN, print board, and I want to get rid of them here. Okay, so white to move. Okay, also white to move, and here is black to move. Well, let's put just want to know if probably, yeah, I just want to go for custom let's have some custom castling and side settings for the last two positions. So this one was white. Well, let's put this to black. Let's put this to white. Okay. Oh, by the way, yeah, it's really, we just don't really have any castling here because both king has castled. Yeah. Okay, anyway, just side to move the last one here. I just set it to white. Okay. No in peasant, no castling. So let's say black and castle queen side. Okay. Yeah, this is parsed. And here can castle king side for both colors. Okay. And here are all available. Okay. And if I just set a new in peasant, let's say a3. Okay, we got this in peasant a3. Okay, here in peasant a6. And one last thing, I just want to make sure, so if I just shift them, so to make sure that in peasant would be reloaded to no square, and paste. Okay. So in peasant a3, okay. Then here in peasant to no square, the castling rights. Okay, so now I'm satisfied. Okay, and the castling, custom castling rights here, e6 in peasant. Okay, so just one last time, let me check if I do reset everything here. So resetting the bitboards to reset the position, reset the occupancies to reset the occupancies. So side to move, but it would be set up anyway because it can be non-white or non-black. In peasant square is set up to no square, and castling is set up to 0, which means to no side is no side can castle nowhere. Okay, so if any, it would be BITBOARDS and initialized respectively. Well guys, so I really think that now this is actually it for this video, and I'm just wondering what kind of position is it printing at the very end here. This one, tricky position here. Yeah, it's printing the tricky position. Occupancies. Yeah, this is quite pretty nice. Well, okay guys, so this is it for this video. This was quite pretty important function to implement, because from now on we are already capable of testing our move generator and probably square attack function as well, with using the custom FEN strings, which is incredibly handy and comfortable to work this sort of way. So yeah, again, like I really appreciate you taking your time watching and following this series. Thanks a lot. I'm very grateful to you guys at this point. I wish you all the best, basically. So probably in the next video we're gonna start and actually hopefully implement the square attack function. I will also quickly walk through the entire source code to make sure everything works as expected, and then we'll go for implementing our square attack function to answer the simple question whether the current given square is attacked by a given side. It would have been needed in order to keep tracking of the king if the king is in check. So just to keep track of that in check state. That's why we need this square attack function, and then hopefully we'll go for our move generation. Well, okay guys, so this is it from my side. Again, like for the third time probably. Yeah, I wish you all the best. Until the next time, and take care. Cheers.